Hello.
Nope. I can only capture my voice.
Okay, wait. Okay. Hello. Yeah. Rishi, don't fret about it. I think I've got this. Don't worry about it.
Uh-huh.
All right.
Yeah, okay.
Cool. Okay, no more delays. Let's get to the point. Thank you for being here, everyone, and let's get to Lagrangian mechanics. Right. So, before I even begin, these are all the books that I've read on this topic, and this pretty much represents my personal progression. I started here, and this is one of the most readable books. It reads like a bedtime story, and this is how I've sort of progressed with this particular topic. And I would sort of recommend doing that because this book starts with assuming you don't even know calculus, and by the end of this progression you'll learn a lot. If you're only interested in Lagrangian mechanics, the specifics would be this book, chapter number 7. And the rest of the books are basically, the most part of those rest of the books are Lagrangian mechanics. So that would be useful as well. And what is the motivation for Lagrangian mechanics? Well, much similar to anything in physics, it stems out of really just frustration in certain aspects, because the trouble that we've always had with the Newtonian approach is that it is, it's based on vectors, it's based on these arrows, and sometimes problems can just get really, really difficult when we're trying to follow the Newtonian path. And sometimes we've learned, especially through studying special relativity or general relativity and other areas of physics, that this can just be downright incorrect, right? And this can sometimes only apply as an approximation. So you need a more general framework that sort of you can use to crack upon all of these things, but also something that is equivalent to your first approximation or your simplest approximation, but is also easier in a few senses. So I say easier with quotes. So that is our motivation for learning about Lagrangian mechanics. And you might have heard this term if you've ever come across any pop science article. You would say that entirety of physics is written in Lagrangians, and so on and so on. And we're going to crack upon this odd object, what it means, what is it, and how does it achieve a general framework that's easy to use, that sort of spreads across all of physics, right? So it all starts with what is called the Hamilton's principle. And the Hamilton's principle, before I even state what it is what is called a postulate. And a postulate, much like anything, is something that we take to be true, right? It's something that we assume to be true, and everything that follows from it also sort of in a sense is logically coherent to its assumptions, right? So for example, in special relativity, we assume that the speed of light c is constant. You no matter what reference frame you pick, if you have a beam of light, it's going to be traveling at the speed of light. There's no change in that. Or that the laws of physics hold no matter which reference frame you pick. Those are all postulates. Those are all things that we take to be true. Similarly, Hamilton's principle is something that we take to be true, and it's something that is of the type. It's a principle of the type that is minimization. It's a minimization principle. Well, we come across minimization principles primarily in optics, right? So in study of optics, the first minimization principle was given by this guy called Hero from Alexandria, ancient Greece. What he said was, okay, let's say if I have light that is, this is water, And if I have a light ray going from here to here, right, I'm going to do my best to draw. What path will it take? That was the question that really was motivating this guy. So this is theta1, theta2, or the other way around, whatever labels you put. So what path would it take? So Hiro actually suggested that it would take minimum distance, right? That was his idea. Well, the cool thing about this is he got the laws of reflection right. Reflection was perfect. He got really well with that, but refraction not so much. So another person, the early, I think, 1600s, who was a French mathematician by the name of Fermat. This is something you might have all heard of. Fermat's principle of least action. So Fermat sort of defined it saying least, he said least time, in a sense, in a very loose sense. What did Fermat mean by that? So if I have such a setup, right, and I'm only going to, okay, so this is my y-axis, all right. So I'm gonna set this to 0, and this is plus y, and this is minus y, right? So this is my y-axis, and obviously I can. There's a specific refractive index for this media. There's a specific index for this refractive index for this media. And let's say I have a point B here, and there's a point A here, and I want my light beam to travel from here, and it's going to cross these two media. What's the path that it's going to take? And Fermat basically said, hey, you know what? Just take this integral. And this is a rather bizarre integral because n of y basically means my refractive index at that given point. And he said, take the distance. And the distance is given by this formula from calculus, please remember. And then just integrate this and equate it to 0. And if you solve this, he said, you would find the path. That is to say, you must minimize this whole thing. You must make this go to 0. Well, in the okay, so this is just a shout out to my last talk, which is well, if we just naturally continue deriving from this point onwards, you'd actually end up with Snell's law. Like boom, you out of nowhere, Snell's law would just pop out. So this is the power of these minimization principles in general. So you have a postulate, and you work from that, you get a quantitative law, right? And Hamilton's principle is rather a very special minimization principle because it relies on extrema, which is to say, what does extrema mean? Well, extrema is in math speak, it's basically just minima or maxima, right? So basically, you take the first derivative of any function with respect to some variable, and equate it to x. You can just find out the minima, the maxima, right? So what happens here in Hamilton's principle is Hamilton said that in general, for a particle, what path would it take? There was a question that was going on in a lot of people's minds. So you have the whole Branke-Stone problem, which is to say, if I have a point A here, point B here, what is the path that it would take such that it takes the least amount of time? And once again, this was solved by this whole method of minimization again. There's a brilliant 3 blue, 1 brown video on this as well. Check it out. So, well, what did Hamilton say? What path would it take? He basically said that the path it would take is the path that minimizes this integral. Well, so let me explain this. So he said this integral, as in the integral of the potential energy, the kinetic energy, which is represented by D, minus the potential energy, integrated with respect to the variables it is dependent on. So I'm assuming that T is a function of x dot and U is a function of x. All right. So what does it mean? So what does delta, or let me draw it again. what this delta basically means is it's telling me that if I take a small deviation, or if I take, or this delta in formula speak is, it can, in a sense, you can just write this delta to be, oops, yep, to just be first derivative with respect to some variable alpha. And I'll explain this in a moment. So this is basically what Hamilton's principle is. And everything Lagrange did after, Lagrange is another mathematician similar to Hamilton. What Lagrange did after this was he figured out what do these equations look like inside here, and how do I talk to Newton's laws. That's what he did. So if I apply this principle, do I get Newton's law? And the answer is actually yes. And we'll see how. Right. So I actually brought in this really weird alpha. So I want to explain that first. So I'm just going to first do some reformulating, which is to say rewriting things in a different fashion. So you had a t minus u, and I'm going to write this as L. Okay, so my L is actually that rhymes oddly, it's a functional. And what is a functional? It's a function of a function. And why do I say this? Because t and u, as we saw earlier, t is a function of x dot, u is a function of x. So this is just a function of these two functions, right? And you also throw in the occasional variable t, so that you can talk about it all throughout time, moving forward or backward in time. So what I'm going to do here now is similar to what's given in this diagram. So I just want to find out the path it takes, right? So I want to first create a small perturbation, and it is given by a few limitations. So first of all, there are these two limiting points here. So I want to go from A to B, right? What is the path that takes from A to B? And I can rewrite my independent variable x here as x naught alpha neta of x. Okay, so a few things here. My alpha is just a weighing parameter, right, for this small deviation. My neta is basically telling me where on this line it is. And this is basically sort of telling me this width, in a sense. And there are a few conditions for neta's existence, and the conditions are neta must be 0 at x1 and x2, or the starting and end points, neta must be 0, and it must be continuously differentiable along this whole path, which means I can differentiate this along this, right? So here's what we do. Let me first so what we were seeing earlier was this. We saw that if I differentiate this, it must go to 0, right? So first let me do that. So I have L here. So if I so I want to differentiate this entire thing, and I can just call it dou L by dou alpha. And I really just want to find out what x with respect to what equation with respect to x do I get when I differentiate dou L by dou alpha such that alpha heads to 0. All right, so this is the whole point. This is, yet again, like I said, this might seem out of the blue, it might seem out of the box, and it is in a sense out of the box because it's just a postulate. And the reason we're using this postulate is, in a very, very raw sense, at least to the best of my knowledge, is because of this excuse. That's it. It works. It kind of hurts to say that, but it does work, and it does work for a lot of phenomena, as we'll see, in the rest of the lecture. But for now, I just want to differentiate this, and my L is a function of these three variables, or these two being independent. So I can sort of rewrite this as 12. Oops, yeah, dou alpha, dou L by, yeah. Yep. So, yeah, so you get the point, right? So remember that this is all inside an integral, and we want that to go to 0, right? And we have this equation here, which is giving us this small perturbation. And we can sort of find out what these two mean. So if I just differentiate x with respect to alpha, I'll get neta. If I differentiate x dot with respect to alpha, I'll get neta dot, because uh, so delta x, sorry, dou x by dou t. Yeah, wait a second. Yeah, dou x dot by dou alpha is nothing but dou by dou d. Oops, sorry, dou by dou alpha times d by dt of x. Right, so I'll just get a neta dot here. So if I apply this equation here, I will get dou L by dou x times neta plus dou L by dou x dot times neta dot. And this is all inside an integral with respect to time. All right, so this is, so I just want this to go to 0 now. But since we're inside an integral and since we're bounded by these two starting and end points, I can actually integrate by parts for especially this one. Let's just integrate this guy by parts. So if I integrate this guy by parts, I'm going to call this point B, I'm going to call this point A. And if I integrate this by parts, what I obtain is basically dou L by dou x dot neta, and I have my limits, and yeah, so what would I get you? So I get dou L by, I would get neta times, what would I get here? Anyone? What's the term that's going to have pop in here? Guys, can you hear me?
Yeah.
Okay, so what do you think we'll get here? Yuvraj, any clue?
I couldn't guess now.
Okay, so
integration of u dv.
Okay.
Just figuring out the which comes.
Okay, very simply put, you'll get this guy, d by dt times dou L by dou x dot. Okay, because this is my u, this is my dv, so I'll get uv minus v du, and du as in I have to differentiate this with respect to time, my variable of integration. So that is why I get a dt here. Now here's how this entire clumsy thing simplifies. Because I gave you these two conditions for neta. One is it must be continuous, and the other is that at points A and B, my neta must vanish. It must go to 0. So at both of these limits, this goes to 0. So this guy is out of the picture, and I only get this guy. I'm only going to get minus neta times d by dt, this whole mess. All right. So, yeah. So I've got this guy. So this is the only term that survives from this. So if I combine it with my dou L, I'm just going to ignore the integral for now. I'm just minimizing this, and upon minimizing this, I will find that dou L by dou x minus d by dt dou L by dou x dot. I'm just taking the neta outside because it's common to this guy and this guy here. The neta is common, and I've not written the integral on both sides. Don't mind it. So here's the thing. My my neta can actually be kind of arbitrary as long as it follows those two conditions, right? So if I truly want the terms inside the integral to go to 0, it is not neta that must go to 0. It should be the terms inside this bracket, logically speaking. So this basically implies that dou L minus dou X, dou L by dou X minus d by dt dou L by dou X dot. This is the guy that goes to 0, and this is exactly what this equation is called. This is basically the Euler-Lagrange equation, and this is the equation I get when I minimize my Lagrange. And again, this is probably a bit of physics speak, but minimize is really a misnomer. People keep saying minimize, but it doesn't have to just be the minima. I think Yuvraj had pointed this out earlier during Chinmaya's lecture as well. It doesn't have to be a minima. It can be a maxima as well. So the right word would be extrema or stationary. So, I mean, the principle of stationary action doesn't sound too much fun. Maybe that's why we didn't go with those words, but this is the right set of words that you would use. So right now, what we've got is we've got a principle that led to a rule that we see here, an equation that we see here. But let's put this to the test as we should. Right, so we'll take a we'll take a harmonic oscillator, right? And I'm going to try to draw a straight line. Yeah, I'm going to split this into two different columns, and you'll see why. So I'm going to use my Cartesian coordinates here. All right. So what is the kinetic energy of a harmonic oscillator, and what is the potential energy? Anyone? Of a single dimension, please. Let's not get too complicated. Guys, any thoughts on that?
You want kinetic energy or the potential energy?
You can tell me both or either. Anything.
Okay. The kinetic energy is half of mv squared.
Yes, exactly. And I'm just going to change the notation a little bit. Okay?
Yeah.
Precisely the same thing. What about you?
Then it depends on h, like the distance. So
it depends on x in this case, since it's basically moving in one direction. All right, since it's oscillating in one direction, it would just be half k x squared. This is it. And this way of expressing a potential, this is called quadratic potential. So it's a very fancy way of saying my potential is dependent on x squared. Okay, so here's the thing. Now my Lagrangian would just be t minus u, which is equal to, taking the half outside, is nothing but mx dot squared minus k x squared. All right. Now I'm going to see if I get the same equation if I follow this path from my familiar Lagrangian equation. So just going to see if that works. So I'm going to take dou L by dou X. So dou L by dou X, it's not going to happen to t because remember, this is independent. Although it is just the derivative of x, we treat this as a separate variable. Right? So dou L by dou X would simply just act on u, which would give me 2kx by 2, which is nothing but kx. And if I want to find out dou L by dou x dot, I go back here, similar procedure, and I will get mx dot. Now, according to the Euler-Lagrange equation, this whole thing, this is how it is supposed to be, right? So now I just need to take the time derivative of this guy. So if I take the time derivative of this guy, it's pretty easy to see that I just got this. And this is a very familiar equation to all of us. And we just assumed, we just had a postulate and we had a equation that can get us the equations of motion, right? And if you want to know the path it travels, you just, again, you minimize this, you'll get the path it travels. This isn't very, great or something. It's just that, okay, we've gotten to what we already know in a very slick or a very in a very easy sense. One moment. Okay, so what this? Okay, so we just saw that it was very easy to do. That's all. But let's try something else. I'm going to change my coordinates. I'm going to go to my coordinates, comma theta. Okay, this is just polar coordinates, right? And I'm going to try the same thing, and it would look something along. Correct me if I am wrong. Okay, so what is the equation here? So this would be mgl 1 minus cos theta. And I think this, okay, what would the kinetic energy be? Anyone? Guys?
I'm not that good in Cartesian coordinates.
I'm sorry? You're not okay.
Theta dot square with the components m theta dot square.
Okay, we're getting closer. Okay, so how many of you think it's m theta dot square? Half m theta.
Half or something. Like I'm not sure of the number.
Okay. Here, okay, so let's just say that it's half m theta dot squared for a moment, and let's just think about this for a second. Why do you think this is wrong? I'm going to ask you guys, why do you think this is wrong, or why do you think this is right? There's something missing here, in my opinion. But
Like
why?
Jacobian?
Did someone say Jacobian?
Yeah,
Okay.
I did.
Yeah, you can use the Jacobian matrix to go from, you can totally do that. You can just totally write x is equal to L cos theta, or you can do that. I don't want to do that. I'm just gonna ask you guys, what is t, right? Let's not go through the whole conversion process. Okay, a very simple way of thinking would be that just a little bit of dimensional analysis, because what is, okay, so if I'm representing circular motion, it would be L theta dot, right? My velocity.
Okay, yeah, we need to consider the distance from.
And
the
if you square this, you just get L square theta dot squared. So it is nothing but half mg theta dot squared and L square. So L square theta dot squared. Yep. So this is my Lagrangian, and once again,
Yeah, just considering kinetic energy, but why is the term g like it's m v square, right?
oops, yeah, sorry, that's a mistake I made. Thank you. Yes, ml squared theta dot. Yes, precisely. Sorry. So we can then write the entire Lagrangian as something like ml squared theta dot squared half mgl 1 minus cosine theta. Oops. Cosine theta. Now, here's the trick. If I treat theta and r to be, L to be just this in a similar sense, a coordinate like this, I would get something like this for dou L by dou x. Instead of dou L by dou x, let me just do dou L by dou theta. So dou L by dou theta would look something like 2ml squared theta dot by 2, and this would just go off, right? Oh, oops! No. Sorry.
But we can't.
Yeah. Sorry. This term won't pop up. So instead, you'll just be differentiating this, and you differentiate cos theta, you get minus sin theta. So yeah, you'll get a minus mg L sin theta. Am I right in saying that? I hope so. Now, again, with respect to theta dot, I do ml squared theta dot by 2. Oh, oops, no, not the 2. Yeah, the 2 would go off. Yes. So now I just need to take the time derivative of this, which means this would just become ml squared theta double dot. And sort of rewriting this would just be dou L by dou theta, which is minus mgl sin theta is equal to ml squared theta dot m goes away, and I would just return to my very old-fashioned, g by L sin theta, which is pretty, we all have seen this, right? So here's the weird thing. So I did transform coordinates, but I didn't need to change my approach, right? So that is something that's really powerful about the Lagrangian formulation, which is even if I did sort of change coordinates, even if I did shift coordinates and express things differently, my approach is still the same and my minimization principle still works. All right. So this is one of the key, important things that the Lagrangian framework provides us with.
How did you equate change in Lagrangian with respect to theta?
I'm sorry.
To
yeah. So So what I did was I basically assumed I just used Lagrange's equations. I just said that what if I just treat theta just like x? Okay, so I have obviously changed my coordinate system, and in a sense, the physics in both of them are the same, right? But what if I treat my equations to be the same as well? Instead of x, I just shove in theta. So that was.
That's fine.
That was and I just 1 second. So yes, that is and that's how I sort of shifted this. And in fact, you can take this one step further and do this thing that's called generalized coordinates, which is just a very, very fancy way of saying, instead of saying, instead of saying I have a set x, y, z, so on, and I have a set, as we saw, x dot, y dot, z dot as an independent parameter, I can just sort of group these and sort of just equate it to something very general. And the letter that we use as a placeholder for any coordinate of a coordinate system is qi, all right? And for velocities, it's qi dot, all right? And the reason we can do this is because my approach has not changed. The equation I used is still the same thing. There's no real distinction. So I can, in a sense, rewrite my Euler-Lagrange equation as dou L by dou Qi is equal to d by dt of dou L by dou Q dot. So, and these coordinates are what is called generalized coordinates. All right, but this also presents something very profound, which I'll get to in a moment. But before that, let's just throw in a little bit of lingo or a little bit of simplicity. This thing, we sometimes write it as PI, and it is called conjugate momentum. This is just a fancy word for saying the partial derivative of the Lagrangian with respect to qi dot. All right, so you can sometimes write the Euler-Lagrange equation as follows, or I like to write it in a line. This is the same thing as this partial derivative. So this sort of fits in one line, and and there are various other ways as well. But this is a term that people sort of throw around pretty commonly, right? And as I said earlier, this is quite a profound shift. This generalized coordinate approach, and then you have t that's flying around, which you integrate with respect to, because we've actually gone from physical space to some other space, which is called configuration space. So if I have n objects in my system, I will need 3n configurations, or 3n dimensions for what is called my configuration space. And the reason why I have 3n dimensions is you can sort of visualize for a single particle the following diagram. All right. So you can see that you really need 3 independent axes to represent the motion of one particle according to Lagrangian mechanics. So this is sort of a very different shift from what we did earlier in the SR series. We went from Euclid to Minkowski, right? Oops. This isn't the same thing, because there is some physical significance to Minkowski space, which is something that I'd like to stress on. There is because in Minkowski space you have the time axis, and a lot of things revolve around it, quite literally so. So what's different, however, is that both these spaces are the same thing. Whatever happens in physical space happens in configuration space as well. There's no profound physical difference, but it's just that when we come here, this approach, as we've seen earlier, it's easier, it's more general, easier to move between quadrants. So there's no physical shift between these two approaches. It's just that we formulated each other differently, and that's why it's called the Lagrangian formalism, and it does not present a theory of the world on its own. It is just a way of writing things. It is just a mathematical way of going about it. Right? So this is something that we should keep in the back of our heads. And again, there are a few constraints to Lagrange's equations when they are written form. Right? So here's the thing. Forces acting on the system must be derivable from potentials. And the way I would sort of argue for this point in terms of analogy is that if you observe these two derivations carefully, this dou L by dou theta term almost always seem to represent my force and the other side. So this is literally just sort of writing in a very loose sense. So that's one way of sort of arguing for this point. It must be derivable from potentials. And again, there's a few more subtle points here that the maximum you can go is quadratic or powers of 2s. If you go beyond that, things get a little bit more wilder, which I'll discuss later. And the second requirement is that equations of this quote-unquote constraint must be relations that connect coordinates of particles and maybe functions of time. Okay, this is rather a very mouthy paragraph. What does the word constraint mean? Any guesses before we even get started on what it is? Guys, Apurva, Yuvraj, anyone?
Yeah, it's like the particular object can move only in this direction, or it's
Exactly.
Circular motion, then it's motion is restricted to a particular. It's a constant distance transverse.
Exactly, precisely. You stole my example as well. So I was just going to tell you guys that. So if I have a rotating bob of this way, a constraint to its motion would be saying that it moves its path is in the form of a circle. So how do I say that its path is in the form of a circle? I say that if I add up all of its coordinates and subtract its distance from the center, which I'll consider this to be O, it must be 0. This is basically the circle equation in a very loose sense. That is, if I take my origin to be 0, right? So this is a constraint. Another form of a constraint could be something along the lines of, I have a ball rolling down. I am going to assume that it is sort of sticking to the plane in a sense. Going down this way, it isn't sort of moving around, even if naturally it does, but ideally, we're assuming that it sticks, right? And these equations must be relations that connect the coordinates of particles. So that's what we've seen here. Must be relations between these coordinates, and coordinates is in the sense of, this is my set of coordinates from now onwards. Whenever I say Lagrangian mechanics, this generalized set is what you should be thinking of, right? And they sometimes may be functions of time. They sometimes, as in Qi, obviously Qi dot is a function of time, but Qi needn't be so. But sometimes they can be, these constraints equations can be functions of time. So to throw in a bit of lingo, there are 3 types of constraints, which I think would be useful if everyone knew what these fancy, weird words meant. So yeah, so holonomic is basically just this. What is holonomic? Which means that these constraints are formed by a relationship between these coordinates. Nothing more, nothing less. But it doesn't really say anything about whether or not it is a constraint that moves in time, or is it a constraint that moves forward or backward, right? So now, if I have a constraint that is not dependent on time, that to say that these constraints, they are not functions of time, t is excluded, it is called scleronomic. And if to say that these constraints are moving with their own sort of, or changing in their own sort of velocity, obviously I want this to be linear, I would then say that these are rheonomic. All right. So this is just some lingo to spice things up, or when you get going on depth study here, it would be useful. I might be mixing which two. I'm sorry. Rheonomic and scleronomic. I think I've swapped this. Amarjit, would you like to, can you speak up a little bit? You can unmute yourself. Yeah. Amarjit? Okay.
Hello.
Yeah, I can hear you.
Yeah.
Go on.
So I was saying that holonomic is different from scleronomic and rheonomic. So like scleronomic and rheonomic comes under one kind of classification.
Okay, as in like what sort of type would it come under?
Very different.
What would it come
Holonomic and non-holonomic are same. Like
What?
fall under the holonomic and non-holonomic fall under the same type of classification.
Okay.
That is done on the basis of integrable.
Okay. Integrable constraints or non-integrable. Okay, right.
So, integrable ones are holonomic and non-integrable ones are non-holonomic.
Okay.
And then scleronomic and rheonomic is a separate kind of classification where you take the time
dependence or not.
Yeah.
Okay. So this would be not explicitly dependent on time, and this would be.
Can you give us like examples for the integrable constraint and a non-integrable constraint?
Well, okay. So, and how do I put it? Okay, so in a very raw sense, integrable. Okay, Amarjit, would you like to add in here as well? So, in a very raw sense, integrable constraints are ones that you can. So you use differential equations to express integrable constraints, and you use a different form of equations to express non-holonomic constraints. So that is what I would leave it at, because I don't really want to complicate things. And there are examples in the books, you guys can look that up. But to put it simply, you would use, I think, difference equations for non-holonomic constraints and differential equations for holonomic constraints. Amadhi, have I erred anywhere along those lines, or do you have something to add on?
Yeah, about the examples of holonomic and non-holonomic.
Yeah.
I'm not familiar with any. Like,
Yeah.
came across this just in yesterday's lecture. So yeah, like I look into it.
Yeah, same.
But yeah, it has to do something with like the what q dot being dependent on time or something. I'm not sure, but it has to do something with q dot.
Okay, but here's the thing. Okay, again, I went through a few of the examples, and almost all of them point towards holonomic. So, and in another sense, I'm not too sure about this, but I'll link up the video and you can watch it yourself. There's this one lecture in MIT that was saying that the degrees of freedom being more than the number of coordinates, which is to say degrees of freedom as in the number of ways you can, for example, if you have a ball that is rolling down, you should only have 2 degrees of freedom, down or up, and you have only 2 coordinates. And that is it's not a constraint per se, but that is to say that my number of coordinates is just equal to the number of degrees of freedom. But if I have a spinning ball that is moving in down the slope, it's got a new degree of constraint, because it can now go this way or this way as well. So that has something to do with whether something is holonomic or non-holonomic as well. Again, this is just my cup of thing, and I'm not very clear about this. So maybe after this lecture we can go through this, or if you want to, we can also stop in the middle and go forward with it. All right. Or Apurva, do you have something to add on here? Do you have any example or anything of that sort?
No, not it. I'm thinking on it.
Mm-hmm.
Not it. I'm not.
Okay. Okay. Right. I will just carry on for the time being, and we'll get back to holonomic and non-holonomic stuff. I encourage you guys to also sort of search up. I'll try to find that MIT lecture as well. All right. And this is something that I've been telling you guys, but I just thought I'd show you guys in a very naive sense what it means. So if I assume what is called rectangular, so where did okay, so I'm not going to bother about that. Let's look at the recording later. But as I was saying, in Newtonian mechanics, the concept of force is pretty inherent, but here we're only talking about P and U, which is just about this single particle or this single body that's here. Well, here's the thing, okay? So you can, in a sense, but the catch is you have a minimization principle, which is the Hamilton's principle, right? And in a sense, it doesn't care about cause or effect, because it's kind of the opposite. It doesn't care about something that's external to the object. It only tells me that the object will travel the path such that this whole integral is stationary. Well, that in a very, very, very loose sense, because sort of constitutes to a purpose-driven sort of a model. So that is to say, its purpose, the whole purpose of any object is to minimize this whole thing. So again, this whole word purpose sort of has theological undertones, and in fact, many of the minimizing principles that were stated in history, other than the 3 which I mentioned, have very much to do with theology. So this is one interpretation of Lagrangian dynamics, but again, it doesn't matter really, because at the end of the day, your theory is still the same. You still get the same results. You still there's no big difference between the two. All right. This is a rather subtle point that's not really important, but just thought I should reflect upon it. Now let's get to conservation theorems. And what I mean by conservation is, we've seen all sorts of conservation theorems. So if I say my angular momentum is r cross p, the conservation of angular momentum is such that L dot is 0. Or if my momentum is given by r dot, r dot, r dot, yes. And then I say that. Right, so these are all the conservation principles that we know of, and obviously have the conservation of energy as well. But before we even go to these conservation principles, I'm going to talk a little bit about what is called invariance or symmetry. What do I mean by, well, both the words kind of mean the same thing. Because what I mean by invariance is if I change my Lagrangian, some Lagrangian plus some delta, which is basically defined as L prime. Invariance basically means my Lagrangian has not changed at all, not a bit. I've made some change internally, but it has zero effect, which is to say that my delta L is 0. This thing is just boom, 0. And symmetry is closely related to this because the way we sort of define symmetry in physics is if I do an action, let's say lambda, on my Lagrangian, but my Lagrangian is still equal, this would just equal Lagrangian dash, Lagrangian prime. But if I say my Lagrangian has not changed after this action, then we can say that the Lagrangian is symmetric under this action. All right, so that's what symmetry means. Yes?
Well, can you clarify what you mean by delta L?
What do I mean by delta L?
What does it mean to change Lagrangian? Are we not just changing the coordinating the or something like that?
I'm sorry, your voice broke. Are we not changing the what?
The are we just not shifting the origin where we first defined our initial Lagrangian or something like that?
Yeah, totally. So my I wanted to take a more general approach first and then go into very specific examples. I can see exactly what you're driving at. Obviously, my delta L can be some change that is some delta R or some my Lagrangian. This Lagrangian is dependent on R or Q or whatever coordinate, and if my normal Lagrangian is expressed as an x comma x dot comma t, my primed Lagrangian can be something along the lines of x plus delta x comma x plus delta x the whole dot. Again, this would the delta x should technically vanish as long as it's not dependent on time, just as a side note. So this is one type of change that I can take, one type of transformation that I can make. But again, there are other kinds or other types as well, which we'll get to. All right. So Amarjeet, have I addressed your point or have I danced around it?
Yeah.
So you can certainly do this. And it's one of the most interesting properties of Lagrangian. Or if you guys want me to hint towards what we've already done, if you guys remember, this was one of the questions which Chinmaya gave us, which is f mu nu. Okay, and now if I make a change, alpha goes to alpha plus dou f. If I make, this is my change that I'm making, does this affect my Lagrangian? And the answer was no. And this change was called a gauge transformation, if you guys remember. Right, so we're doing something very similar here, but I want to drive towards these guys, the guys that we've already met, these characters that we've already met in our journey in physics. Angular momentum, linear momentum, and energy. So these are the three characters that we care deeply about right now. But again, my point would be that I just want to get this idea of invariance or symmetry across, which is if my Lagrangian undergoes no change under a change in my variables, a small tweak in any of these, it is said to be symmetric for that specific change. Okay, this is the general idea. And now let's get to the specifics. So first thing is conservation of momentum, and we have all seen this. And how does it come from the Lagrangian formalism? Okay, so now I am going to say that my Lagrangian is invariant under the action of moving my origin. So if I have my origin here, but if I move it by a delta x, so I've sort of moved it from this position, this position. So this is me moving this whole thing. And to be very, very exact, my change can be represented as delta r, which is to say in all coordinates, is equal to the summation of delta x times the specific basis associated with it. Cool. So this is the transformation that I'm making. So I'm basically saying that if my Lagrangian is dependent on r, I'm making a small shift delta r. And I'm saying that my primed Lagrangian, which I get as a result of this, is just the same as my actual Lagrangian. And we will see how this leads to this, okay? Or why the statement that if I perform a specific action and my Lagrangian is invariant, it is called a symmetry, or why there's a certain sense of invariance and what it means in a larger sense as well. Okay, so now and also a side note, I'm only looking at inertial frames. Don't get me started on non-inertial ones because I have absolutely no clue. Okay, so we're only going to be looking at inertial frames, which means two things that are that should be familiar is space is isotropic, which means it looks the same wherever I look at it, and I can sort of move around, or I can change my orientation of my coordinate system, and it makes absolutely no difference. And it also means time is homogeneous. Okay, I have no idea how to spell the rest, so I'm just going to blabber that out. But this is something that comes bundled with an inertial frame, just so you guys know. And this means I can go forward and backward in time. It doesn't really matter if I go forward and backward in time. My picture or my physics is still the same. All right, just a side note before I begin. Now let's get back to this shift. So I want to express my delta L, which is the change that has occurred to the Lagrangian itself, in terms of this. So I will express it as dou L by dou X. Forgive me, I am excluding the indices, and technically I should exclude this based on Einstein notation, but it doesn't really make much of a difference as long as you get the picture. All right. So here's the change that I am making. And according to our conditions, according to this delta L must equal to 0. Now, let's examine this in a closer sense. Let's examine this in a closer sense. So what I've basically shifted my coordinate system, right? And this is pretty much independent of time. And why is that? Because I can shift now or I can shift later. And I'm just going to perform that shift. It isn't changing across time. It isn't dynamic. It isn't changing across time. So the first thing that you must realize is if I have my delta x dot, it's just the same thing as saying delta d by dt of x. I can sort of take this outside and say that x is not time dependent, and if I differentiate something that is not time dependent with respect to time, I will most certainly end up with 0. So this guy goes home. All right. So thus, if I want my delta L to be 0, this guy needs to be 0. So my dou L by dou X delta X must be 0. This is a necessary condition. Okay, very important stuff. If I want this to be satisfied, this needs to happen. But here's the thing. I am not just considering my delta X along one direction or one particular special direction. I'm going to say that my delta X, any arbitrary delta X, any whatever sort of direction I can take up. Well, here's the thing. If I can take up any arbitrary non-zero or delta x, that would just mean that my dou L by dou x is the guy that is actually zero. If this is arbitrary, then this is the guy that must be zero. And immediately we can go to our Euler-Lagrange equations. D by dt is equal to dou L by dou x dot. Now, this is zero. So if I integrate on both sides, I can then say that my dou L by dou x dot is equal to some constant. All right. And again, if I just play around, again, we've seen that t is a function of x dot. And this would just be dou t by dou x dot. And as we all know, by dou t by dou x dot, it's just the momentum. And I can just say that it is constant or conserved. Okay, so the key takeaway from this is not all the details, but it's just that for a Lagrangian of a inertial frame, if I make a change in my coordinate system, if I move it forward by a delta x, I can see that and say that my Lagrangian is invariant under such a transformation. The conserved quantity that pops out is momentum. All right. Now, what happens to the other character, which is kind of similar, kind of like an older brother kind of character, which is the angular momentum? Once again, just a reminder, angular momentum can also be expressed as L. So I will be using J instead. All right. So it's just something that it's a bit of weird formalism that we learned in our classical mechanics class as well, but here it's kind of useful. All right. Now, the shift I'm going to make is I'm going to make a small shift, delta R. And my delta R is actually nothing but my delta theta cross my R. Sorry. Yeah. So it's pretty obvious why this is true. All right. So this is what I'm sort of driving towards. So this is the change that I am making. And again, the idea is that my Lagrangian is invariant under this sort of transformation. Now, what does that imply for angular momentum is the question. And again, let's do the same procedure that we did, except a little different. So I was actually, a little lazy with this notation here. Not lazy, sorry. So what I could have done is, obviously, dou L by dou x dot is nothing but P. But if I have, again, another assumption to throw in, it does, okay, so just a side note, I'm making this assumption to make things easier for us. It can work with non-rectangular coordinates or orthonormal is the very, very fancy word, which is to say it is orthogonal and that each basis is of unit length, right? So this is one thing. And also another very interesting thing that pops out is the following. So this is something that is followed by rectangular coordinate systems. And if I make that assumption, my job actually becomes easier. So I can actually write my dual will follow the same format because I'm kind of just making an angular shift rather than a shift along a singular direction, right? So what happens is I get the same thing, but I get dual. So I'll just write it out and I'll reformulate it as well. So I get dual by dou x dot delta x dot. Now, reformulating this is basically very simple. So this is my p and this is my p dot for rectangular coordinates. So if I arrange this properly, I'll get p dot delta x plus p delta x. So this is the shift. Let me go to the next page so that there's more room. I got what? I got p dot delta x plus p delta x Now, here's the beauty. I'm just going to substitute this inside. All right. So again, as we've seen, to satisfy the condition, this delta must go to 0. So delta, okay, I don't need to write delta L. So this, I'm going to expand this in terms of this. So you would basically get P dot delta R plus P delta R is equal to 0, which would basically, oh, sorry, I've made a small mistake. X dot delta R dot, and this would basically mean P dot times delta theta cross R plus P times delta theta, or yeah, it would just be cross R dot. A very interesting thing about the cross products is that you can actually cyclically move these things, especially if you have something of this kind that's called a triple product. So I am just going to wait a second. There's a small bit of confusion. I'm just going to take my delta theta out, but here's the thing: since it's a rectangular coordinate system, yet again, there's no such thing as so. If I differentiate R dot delta R dot, I would once again I should end up with delta theta cross delta R dot. Okay, seems a little unjustified even to me, but if someone can justify that, that would be interesting. I don't know why that assumption is made, but we make that. Now, here's the thing. As I said, we can cyclically rotate, so I would just throw in R cross P dot plus delta theta times R dot cross P, and this basically just looks like this. This looks like d by dt delta theta times R cross P. Well, if I want this whole invariance to be true for any arbitrary delta theta, it's this guy that must go to 0, or this whole guy that must go to 0. So once again, if I integrate on both sides, I would end up with something of this kind, and this is it. This is basically the conservation of angular momentum. But what you must keep in mind is this happened when we made a very particular shift to our Lagrangian. So it happened when my delta L was expressed in terms of delta R. So just keep that in the back of your head. Okay, so we've seen two conservation theorems so far. What happens to the guy, the largest guy of conservation theorems, which is conservation of energy? What happens to that guy? Well, that's also something similar and something probably a little bit more profound. And again, it comes with conditions as well. The conservation of energy is just, it's just the same of saying that your Lagrangian is independent of time, which is to say that my potential energy nor my kinetic energy have not changed over time. Thus, their sum has not changed over time. I hope that is clear, right? So, if I say that my Lagrangian is not dependent on time, then I can very simply express the conservation of energy. Oops. Yeah, okay. Is equal to 0. Now, I just need to expand this out in terms of this similar kind of expansion that we've seen. So dou L by dou X by dou T, which is basically just X dot. So yes, same thing. Plus dou L by dou X dot times dou X dot. Here's the thing. Dou L by dou X is nothing but d by dt of dou L by dou X dot, right? That's the Euler-Lagrange equation. So I'm going to substitute from that. So I'm going to substitute d by dt of dou L by dou X dot times X dot plus dou L by dou X dot times x double dot. Right? Here's the thing. It does look like you're basically doing this bit of differentiation, which is dou L by dou x dot. Now, here's the thing. Yep. So I can then sort of, oops, I've made a small error here. This is the total derivative. This isn't the partial derivative. So this would be the total derivative. So if I bring this to the left side, it would then just, this whole entire thing would just read L minus dou L by dou x dot. If you guys remember clearly, this was just the conjugate momentum. So I can express this as px dot as well. And this whole thing is, you can differentiate this, and this can equal to 0. And that means if I integrate this on both sides, I will just get a constant. Now, this has got its own name, which I'll get back to. And it also has a very interesting geometric interpretation. And what happens is, okay, so I've got px dot here, and without going into too many details, let me just write this as t minus u minus px dot is equal to minus h. My h is the constant. Okay, okay, so if you think this minus is arbitrary, that's exactly what I've been thinking as well. It's rather arbitrary, but we're just following some convention here, and I'll explain this in a moment. There's this, okay, so you can refer to this Thornton book, which is given in the bibliography. There's this one theorem that will tell you that px dot for any rectangular system or any closed system, in a sense, is nothing but just 2t. All right, so first I'll take the minus out, which is to say that I'll get minus t plus u plus 2t is equal to h. All right, and u, that just basically means t plus u is equal to h, and this represents my total energy, and this h has a special name. It's called the Hamiltonian. Nice. You guys have probably seen this. And well, again, as we've seen in the previous conservation laws, this resulted from an homogeneity of time, or to say that if I go forward or backward in time, that doesn't matter. My delta L is somehow related to my delta T, is the whole point. So if I say that my Lagrangian is invariant under this action, under this transformation, then I swiftly end up with my conservation of energy. But, and well, again, I did have a condition here, and there was a bit of arbitrariness along this minus sign, but this is pretty interesting to say that, my energy is basically invariance of the Lagrangian when I move forward or backward in time. But it also comes with its own conditions, because we've defined a new object in a sense, and it comes with the conditions that it must be independent of time, which we already saw we sort of assumed it. This is time independent. Thus, and the reason it must be time independent is so that you get your potential is a function that is quadratic, right? That isn't to say that, okay, so this is a side note, that isn't to say that you can't have, other higher order terms. This is not what it is saying, but rather that most cases it does diminish at higher orders, and most cases you wouldn't need higher orders, because these higher order terms usually come under other sort of systems which are dissipative, which is to say that you have energy loss, or you have some damping, or you have some friction or something along those lines, which we've not discussed. All right. And another condition is that the potential energy must be velocity independent, so that this is something that we sort of assumed for the Lagrangian itself, right? So if I have dou L by dou Q dot, it is essentially the same as dou L by, dou T by dou Q dot, right? So the larger point I want to drive at beyond all these pesky details is that if I have a particular action that leaves the Lagrangian invariant, as this table summarizes, it corresponds to a conserved quantity. All right, this is one of the most simplest ideas that you can think of. So if there's a symmetry, then immediately there has to be something that's conserved according to it. All right, and this idea is called Noether's theorem. And it's a rather very large idea in the sense that you need a lot of prerequisite math. You need to know about manifolds. You need to know about this whole other demon that's called Hamilton-Jacobi theory before you even get into this. But its beauty can nevertheless be appreciated by a bystander like me just by this sort of pattern-seeking behavior that we've just shown here. So I've just looked at the pattern and observed that there is a correspondence between the two. Again, if you're interested in the details of the Noether's theorem, I would suggest you try Herbert Goldstein, Classical Mechanics, one of the best, not the best, one of the thickest, biggest canonical texts ever to exist on classical mechanics. And he goes over this on the last unit. Very interesting treatment. Right? One thing that we haven't dealt with, which I just want to allude to and then probably just close the talk because it's 5:45, is what happens to field theories? What's going on here? Because in a field theory, you want to talk about a position in a field. You don't want to talk about the position of a particle. You don't want to talk about Qi or Qi dot. You instead want to talk about something else. So for field theories, you can then sort of write your Lagrangian as follows. And this is a rather very weird thing to write. All right. So bear with this. For a field theory, I have this function phi that describes all of the points. That's a function of all of the points in the field. And I have another function phi, which is a function of Qi dot. And I have, obviously, I need to show some dependence on Qi and T. Okay, so once again, this is the action that this is the action that I would minimize. But there's a small change for field theories, at least for the field theories that we care about, which is in 4 dimensions. It's this integral. It's d4. What does d4 mean? Basically saying dx, dy, dz, dt. All right. So the reason we do that, the reason we have to include these 3 terms, not just this, is because the Lagrangian that we've considered here, this is a bit of a switch in notation. Usually you'd have the fancy L here, you'd have the L here, just so that you know. But the point is, this is what is called a Lagrangian density. Instead of considering a singular particle's Lagrangian, you want to think about the entire field's Lagrangian and its density. And you would need to integrate, obviously, to get across that specific region within those limits. You need to integrate that with all of these 3 coordinates or whatever coordinates of the coordinate system that you're using to obtain the actual Lagrangian from the Lagrangian density. And this is what we will try to minimize when it comes to field theories. And hopefully the next week or the week after that, we'll be able to see this with respect to the electromagnetic field and how you can sort of build Maxwell's equations just in forms of tensors, and why is it Lagrangian of this sort, and what does it mean? What does the word gauge even mean? So on that note, I'd sort of stop with my talks, and we can field more questions.